Okay, welcome back, novice statisticians. This is the second video on Chapter 8, Sampling Distributions is what we're talking about. Okay, that was slide 1. And going to the next slide. Next slide. Slide 2. Okay, some definitions. Sampling error. The variability of a statistic from sample to sample due to chance, right? So I drew those little pieces of paper, right? And by chance, they varied. The means varied. Okay. Sampling distribution, the distribution of sample statistics that we would see if we repeatedly drew multiple samples from one population. That's exactly what we did, right? We repeatedly drew these heights, right, from one population, which is our class. The population of our class's height in inches. Okay, and we graphed it to give a visual representation of the distribution. Okay, and I put a last bullet. If this makes no sense, don't worry. It will make more sense by the end of this class. Okay, so let's look at SAT scores. This is slide 3. SAT scores in the year 2015. So globally, including internationally, 1,698,521 students took the SAT. The mean for the population, so the mu was 1490 out of 2,400. However, for the typical research project in education, we almost never know the population mean and standard deviation. Okay? Therefore, we can't use z-scores, which you just learned about, to estimate how probable a particular value is, because we almost never know, aside from these, large standardized tests, we almost never know. For example, I don't know, the math achievement of third graders in our state. Well, we might be able to figure that out from a state report card or something like that. But generally, we just don't know for our population we don't know for our sample and our research question. We don't know the population mean and standard deviation. However, there are special properties of sampling distributions that make it possible to make inferences about the population, even though generally we don't know the mu, we don't know the sigma. Okay. Slide 4. And we're exploring those special properties in this lesson. So there's a simulation. I'm on slide 4. There's a simulation. So if you click on that link, okay, it takes you to a really cool simulation. And feel free to pause the video and try it. And what I did was I went to that simulation and to make the slides that come next. Next slide, slide 5. Okay, it's a sampling distribution simulation. A simulation that's similar to what we just did with the, the little pieces of paper and writing on the board, but it does it on the computer. So, the population mean length of newborn babies is 20 inches. Let's imagine that the population standard deviation is about 3.5 inches. It's actually more like 1 inch. But the standard deviation of our heights in our class was 3.5. So this graph shows the distribution of birth lengths of newborns. Okay, so that would be the lengths of individual babies, right, in inches, right? So if we had taken, all the babies, let's say in the U.S., and graph their length, that's what you would see. That's a representation of our hypothetical population with a distribution with a mean of 20 inches and a standard deviation of 3.5 inches. So that's a graph of individuals there, right? Okay, so slide 6. Now, if we randomly were to look up the birth records of 5 babies and average their length, just like we randomly grabbed 3 little slip of paper and took the average, and graph the mean length of those 5, then we do the same for another 5 babies, and so on for a total of 5 times. We get that graph that's on top. Okay? The distribution of means. No, we're no longer looking at distribution of individuals. We're looking at the distribution of sample means when we've drawn 5 records from 5 babies. Okay, so you see, it looks like if you look on the left-hand side in blue, right next to the graph in blue, you see the mean of these means. Okay? The mean of these means is 20.47. Okay? You see that? It's not the mean of the individual babies. We're now in groups of groups. We're talking about groups of groups. And so the mean of these means is 20.47. Now, let's go down to the graph on the bottom. Now, if instead of grabbing the birth records of 5 babies at a time, we grabbed the birth records of 20 babies at a time, and then took the average and graphed those lengths, okay? Yeah, I wrote that wrong. Average their length and graph the mean length of those 20, so change that on your slide. Then we do the same thing for another 20 babies, and so on for a total of 5 times. We get the graph on the bottom. Okay, so the graph is on the bottom is the distribution of sample means, right? Where the N is 20. There are 20 individual birth records in each of group that we randomly drew. Here we have our mean of means, our mean of this sample distribution. If you look at the blue on the left, it's 20.18. Okay? So, which is closer to our population mean? The mean when we drew 5 birth records at a time, or the mean when we drew 20 birth records at a time? If you said the mean when we drew 20 birth records at a time, you're right, because we know our population mean is 20.0. When we drew 20 records at a time, we got 20.18, which is closer to 20 than 20.47. Let's go to the next slide. Okay, so last time we were grabbing 5 times we were getting the mean. Now this time, let's randomly look up the birth records of 5 babies, average their length, and graph the mean length of those 5. Then we do the same thing for another 5 babies, and so on for a total of 10 times. Okay, now we're taking more samples. When we did the samples over there, we took 4 samples, right? Over here on the previous slide, we took 5 samples. Here we're taking 10 samples. Okay, we get the graph on the top when n equals 5. Then we get a mean of the means is 20.23. And then if we do the same thing, but instead of drawing 5 records at a time, we draw 20 records at a time. And again, the same mistake on the slide. It should say, if we randomly look up the birth records of 20 babies, average their length, and graph the mean length of those 20, so please change that on your slide. Then we do the same thing for another 20, and so on for a total of 10 times. We get the graph on the bottom. Here on the bottom, yes, you see that graph there? Our mean was 19.86, and on the top it was 20.23. Okay, let's look at another slide. Oh, so which mean is closer to our population mean? If you said the graph on the bottom, you're correct. The mean of the means on the bottom is only 0.14 away from 20, and the mean of the means on the top is 0.23 away from 20. Okay. Next slide. So now I'm on slide 8. Okay, now we're going to draw a whole bunch of samples. If we randomly look up the birth record of those 5 babies, average the length, and graph those means, then we do the same thing for another 5, and so on for a total of 200,000 times we get the graph on top. This is a nice thing because it would take a really long time for me to do that with the little slips of paper, but a simulation on the computer. Computers are fast. They might be dumb, but they're fast. Okay, so yeah, that's what we get that distribution. Okay, and look at that mean, 20.01. So very close to our population mean. And we do have a pretty normal distribution, right? It's fairly symmetrical. A little bit peaky, right? Not really skewed. Okay, let's look at on the bottom. So randomly look up the birth record of 20 babies, average their length, and graph the mean length of those 20. Please change that on your slide. That's what happens when you copy and paste sometimes. Okay, same thing for another 20 babies, and so on for a total of 200,000 times we get the graph on the bottom. So the mean for the bottom distribution is 20.01. Okay, same as for the top. They have the same means this time, both very close to our population mean. But let's look at the standard deviation. When we drew 20 babies, our standard deviation, that's in red on the bottom, was 0.78 inches. When we only drew 5 babies at a time, our standard deviation was 1.55 inches. So we see that when our sample size is larger, our standard deviation of the distribution of means is smaller. Okay, let's go on to slide 9. Slide 9. Okay, so to create a sampling distribution, we basically made a histogram of the mean values of a bunch of samples drawn from a population. And so we were working on our histogram over there on the board, and you saw the simulation graph the histogram for us. If we keep drawing more and more samples, the sampling distribution will get closer and closer to being a continuous normal distribution, which you're familiar with. Okay, slide 10. When each sample has more members in it, the normal distribution has a smaller standard deviation. And we saw that with the comparing when we have n equals 20 versus n equals 5. When it has fewer members in it, it has a larger standard deviation. So, and the graph on the side, which shows the distribution of raw data, right, which would be the distribution of individual baby lengths, and compares it to the distribution of sample means, so the distribution of means of baby lengths. Okay, the standard deviation of a sampling distribution is called a standard error. Okay, so you know how we were writing the error on the board, like for our first sample, we got a mean of 68.3, and our actual population mean was 68.4, and we said the sampling error was -0.1. Well, that corresponds to the deviation in individual unit land. When we're in mean land, we can find what the standard distance is of a particular mean from the mean of the means, and that's called the standard error. It's always smaller than the standard deviation of the population. Okay. And slide 11. Excuse me. So sampling error is the random variability we get when we sample from a population, and we wrote down all of our sampling errors. Usually a sample mean doesn't exactly equal the population mean because we just happen to, just because of the people we drew, we just happen to draw a particular people, a group of people, they happen to have a particular height. It usually doesn't exactly equal the population mean. From the sampling distribution, we see that the error is normally distributed. Okay, so the distance of a particular mean from the population mean is normally distributed. So sampling error is normal and expected. I'm on slide 12. Sampling error is normal, it's expected, we can predict and estimate it. Okay, now in contrast, sampling bias is when you get a problem. Okay, and that's what that first whole column exercise was about. That's when the error isn't normally distributed because we didn't sample randomly. Okay, so if we have an estimated parameter, remember a parameter is just a particular statistic, like a mean. So if we have an estimated mean or estimated parameter, and it has a distribution, when we draw samples, the distribution of those samples should line up with whatever that estimated parameter in the population is. Okay, it should line up. That bell curve should line up. Now, if we are actually drawing samples, if we have bias, if we're not drawing randomly, if we're not making sure everybody has an equal chance of representation in our sample, then our distribution might be quite a ways off from whatever that mean is that represents the true population mean. Okay, next slide. So, and this is the last slide, slide 13 for this part. Using a sampling distribution to answer questions. Okay, so since the sampling distribution is normal, and we know the properties of a normal distribution, we can use it to answer questions that we have, like how, if we get a particular mean, how common do we think that mean would be in a particular population? And this is similar to what we've done with individual z-scores, but soon we'll be starting to be able to compare groups, okay, which is often what our studies are about. We're looking at groups of people, comparing them to other groups of people. The only time you're really looking at individuals is when you're sitting down with an individual child and you're testing that individual child, perhaps for placement in a gifted program or a special education program. You're testing that individual child and you're comparing that one child's score to some norm referenced value, right? But normally when we're doing these, when we're doing our large-scale research studies, when we're looking at things at the school, the district, or the state level, or the national level, we're looking at groups of children, or groups of youth, or groups of patients, or groups of clients, or groups of athletes, or groups of student athletes. Whatever it is that we're looking at groups. And soon we'll be able to start comparing that. Okay. That's all for now. See you soon.